Now we want to define this map delta. So you start with some p1 in kernel of h. So this map is injective, so this p1 sits here, it's in the kernel of h, so it gets mapped to 0 here. Now we have exactness at p1, this is given to us. So this map is surjective because you have 0 coming out here. So this p1 will get lifted to some n1 right here. And then via this map g, it gets mapped to n2 right here. So p1 is in kernel of h. Since beta 1 is surjective, you have some n1, so that beta 1 n1 is p1. That is n1 gets mapped to p1. So let n2 be g of n1. So this n1 gets mapped to n2 via this map g. Now notice that this n2 gets mapped to 0 because of the commutativity of this square. So n1 goes to p1 goes to 0. From here n1 goes to n2, and then here it has to agree on this side. So because of commutativity of the square, n2 will also have to get mapped to 0 since n1 gets mapped to n2. So n2 lies in kernel of beta 2 since n2 will get mapped to 0. Now you have exactness at n2, so that means kernel of beta 2 contains image of alpha 2. So it contains image of alpha 2. So therefore you can lift this n2 to some element m2 here. So alpha 2 of m2 is n2. Now this m2, you modulo out the image of f becomes m2 bar, and this is precisely what we will set delta p1 as. So you set delta p1 as m2 bar. So this p1 gets mapped here to m2 bar. So again it is in kernel of h, so this p1 gets lifted to n1, n1 goes to n2, and n2 goes to m2, m2 goes to m2 bar. So this is the entire process. Now we have to show that this map is well defined. So well defined means that it does not depend upon two different choices of inverse images. So first of all, notice that this alpha 2 is not going to cause us any problem because m2 is unique since alpha 2 is injective. So we are not going to have problem here, but you could have problem at the start. This p1 could have two different images. So say this p1, this map is surjective, so there could be another a1 here in n1 which gets mapped to p1. So say there is a1 in n1 which is the inverse image of p1. Now this a1 via map g, this gets mapped to a2 right here. So you have a2 is equal to ga1, and say this has an inverse image b2 in m2. So this a2 gets mapped to b2 here in m2. Just precisely the same thing which we did with n1. n1 got mapped to n2 and then to m2. Here a1 gets mapped to a2 and then a2 gets mapped to b2. So precisely what we did while constructing the map delta. Now this n1 minus a1, if you apply beta 1 to it, it becomes 0. So n1 minus a1 lies in the kernel of beta 1, because if you apply beta 1 to n1, this is p1. If you apply beta 1 to n1, this is also p1, and p1 minus p1 is 0, so therefore it lies in the kernel of beta 1. So n1 minus a1 will lie in the kernel of beta 1. Now we have exactness at n1. So this n1 minus a1 lies in kernel of beta 1, but kernel of beta 1 is equal to image of alpha 1 because of exactness here. So we are able to lift this element n1 minus a1 to some element m1 here. So that is alpha 1 m1 is equal to n1 minus a1. So therefore we have alpha 2 applied to m2 minus beta 2. So you apply alpha 2 to it, you get n2 minus a2. So we apply alpha 2 to this, you get n2 minus a2. So obviously this will be alpha 2 m2 minus alpha 2 b2, but we lifted these elements here. So this alpha 2 m2 is already n2 and alpha 2 b2 is already a2. So you get n2 minus a2. But this n2 minus a2 is g of n1 minus a1 because this n2 came from n1 and a2 came from a1. So g of n1 minus a1 is g of alpha 1 m1 because this n1 minus a1 we had lifted to m1. So n1 minus a1. So notice right here. So you put it right here. So in fact, you put g in front of here. G of n1 minus a1 is equal to g of alpha 1 m1. That's precisely what we have done right here. But g of alpha 1 m1, so m1 going from here to here, so first apply alpha 1 and then g, is same as first applying f and then alpha 2. So commutativity of this square. So going in the other direction, you first apply f and then you apply alpha 2. So first you apply f and then you apply alpha 2. So this gives us this equality. Alpha 2 of m2 minus b2 is equal to alpha 2 of f m1. Now alpha 2 is injective, so this part is injective. So you get m2 minus b2 is equal to f of m1. So that is, if you modulo this out, then you will just get m2 bar. Because both of them, they lie in the same equivalence class because you modulo out image of f. So both of them are the same in, so m2 minus b2 is the same in this co-kernel of f. So m2 is same as b2 in co-kernel of f. And that is precisely what we wanted to show, that this does not depend upon two different choice of inverse images. So even if you have two different choices, here we have two different choices, n1 and a1, they will get mapped in such a way that once you have the equivalence class, it would not matter. So if you have different choices, they will get mapped like this, and then again it will come to the same equivalence class. So therefore this map is well defined. So we are going to show exactness at kernel of h. So the first thing we will show is that image of beta 1 tilde lies in kernel of delta. So first recall how this map delta was constructed. So we took an element p1 here. This map is injective. This p1 got mapped to p1 here. Then we lifted this p1 to n1. This n1 went to n2. This n2 came to m2, and this m2 became m2 bar. Now what we are going to show here is that if p1 lies in the image of beta 1 tilde, then this p1 will get mapped to 0 here, this 0 will get lifted to 0 here, this 0 will get mapped to 0 here. So that means if you apply delta to p1, you get 0. So p1 will lie in kernel of delta. So to show this, so you start with p1 lies in image of beta 1 tilde. So p1 lies in image of beta 1 tilde. That means p1 comes from some n1 right here, and this map is injective. So this n1 gets mapped right here. But this n1 is coming from kernel of g, so this will get mapped to 0. And now you have the procedure. So 0 will only lift to 0, which will go to 0. So p1 lies in the kernel of delta. Again repeating, p1 lies in image of beta 1 tilde. This means p1 comes from some n1 which lies in kernel of g. And this n1 is the inverse image of p1. So this n1 is the inverse image of this p1. And then you can see this n2, this n1 gets mapped to n2 here, which has to be 0 because n1 lies in the kernel of g. And therefore you will have delta of p1 is 0, because if n2 is 0, then this m2 would be 0, m2 bar would be 0. Now we show the opposite inclusion. We start with p1 here in kernel of delta, and then we will show this p1 comes from some beta 1 tilde. So that is, if you start from p1 here, it comes from some element here if you apply beta 1 tilde to it. So first recall how this map delta was constructed. So you had p1 here, this got lifted to n1, this n1 got lifted to n2, here you went to m2, and then you went to m2 bar. So p1 lies in kernel of delta means that p1 will get mapped to 0. So to get to map to 0 here, that means it has to lie in image of f. So that is m2 should come from some image of f, only then it will get mapped to 0, because p1 is getting mapped to m2 bar, and for m2 bar to be 0, that means m2 has to lie in image of f. So m2 has to come from some m1 right here. So now notice this square commutes. So in this square, m1 gets mapped to n2, you go to alpha 1 and then g, you get mapped to n2, and n1 also gets mapped to n2. So applying alpha 1, you get alpha 1 m1. So both n1 gets mapped to n2 and alpha 1 m1 also gets mapped to n2. So if you subtract them, then it will get mapped to 0. So more formally, you have g of n1 is n2. So n1 gets mapped to n2. Now n2 is same as you first apply alpha 2 and then f to m1, because n2 was alpha 2 of m2 by our construction of delta, and m2 is f of m1. Now which is equal to, instead of going from here to here, you can go from here to here. So first apply alpha 1 and then g, so you get g of alpha 1 m1. So notice that this is also n2 and this is also n2. So n1 minus alpha 1 m1 lies in kernel of g, because if you apply g to it, this gets to n2, this gets to n2, n2 minus n2 is 0. So this lies in the kernel of g, and that is precisely what the elements we get here. You get n1 minus alpha 1 m1, and this is precisely the element we were looking for. So you apply beta 1 tilde to it, it will get mapped to p1, and you will see this beta 1 tilde to this is same as applying beta 1, because beta 1 tilde is just a restriction map of beta 1. So you get beta 1 n1 and minus beta 1 alpha 1 m1, but this is a exact sequence at n1. So image of alpha 1 lies in the kernel of beta 1, so this gets mapped to 0. And you know already that beta 1 of n1, so this n1 you lifted from p1, so beta 1 of n1 is just p1, and we are done. Now we are going to show exactness right here. So first we are going to show that image of delta lies in kernel of tilde of alpha 2. So you have alpha 2 tilde right here. So we are going to say image of delta lies in the kernel of alpha 2 tilde. So first recall how this map delta was constructed. So we started with p1 here. This p1 came to p1 here. You lifted to n1 here. This went to n2 here. This went to m2 here, and this went to m2 bar here. So notice that this n2 is actually an image of n1, and this n2 gets mapped to n2 bar here. So what does this alpha 2 tilde do? It maps m2 bar to n2 bar. But this n2 bar lies in the image of g, because this n2 comes from this n1 via this map g. So if you are getting n2 bar from m2 bar, it has to be 0, because you modulo out image of g. So more formally, if you start with m2 bar lying in image of delta, this implies alpha 2 tilde of m2 bar is just n2 bar, which is 0, because this n2 comes from image of g, since n2 lies in the image of g. So this implies this m2 bar lies in the kernel of alpha 2 tilde, and that's what we wanted to show. Now we want to show the opposite inclusion. So we start with some m2 bar here, and we will show that this m2 bar comes from some p1 which lies right here. So this p1 will get mapped to m2 bar here. So notice that this m2 bar is coming from m2 here. So now notice that we are saying that m2 bar lies in the kernel of alpha 2 tilde. So alpha 2 tilde is right here. So this m2 bar is getting mapped to 0. So that means it is getting mapped to 0, which looks like n2 bar. So this n2 bar comes from n2. So this is 0 in n2 bar means that this n2 has to come from some n1 here, because this n2 lies in image of g. Only then when you modulate it out by image of g, you will get 0. So we are saying this n2 lift to some n1 right here. Now beta 1 acts on this n1, and that will give you some p1 here. So let us recap what we have done. You start with m2 bar lying in kernel of alpha 2 tilde, and then you said that this n2 has to contain image of g, because if it is 0 here, it is because you have modulo out with image of g. So therefore this n2 has to come from n1 here, but by the construction of our map delta, this n2 also comes from alpha 2, which applies to m2, because after all, this alpha 2 tilde is just coming from alpha 2. So we have this diagram also commuting. So alpha 2 of m2 is giving you n2, and g of n1 is also giving you n2. So n2 is equal to alpha to m2 by our construction of map delta, and we have been able to lift n2 to n1 because you are modulo out by image of g. So now you set this p1 as equal to beta 1 n1, and here there will be the end of the story. If we are able to lift this p1 to p1 here, then we are done, because then we have found an element p1 here which gets mapped to m2 bar. So we have to show that p1 lies in kernel of h. So that is h of p1 is 0. So what is h of p1? So h of p1 is lying right here. So this h of p1 comes from n1. So you apply beta 1 first and then h to it from n1. So it is coming from n1, commutativity of this square, but you could go from here to here also. So you could first apply j and then beta 2 to get to hp1. So first apply g and then beta 2. So instead of g n1, you can write n2 here, but you know that this n2 is alpha to m2. So this n2 is nothing but alpha to m2. So instead of n2, you're writing alpha to m2. Now beta 2 alpha 2 will be 0 because of exactness here. So image of alpha 2 lies in the kernel of beta 2, so this will be 0. So therefore you get h of p1 is 0. So p1 lies in the kernel of h, so you can lift it up right here, and you can take m2 bar as the image of p under delta. So notice that the way we have done the proof is that if we delete two arrows, so say if we deleted this arrow is no longer there, then this arrow will also be no longer there. Everything else will go through. If this arrow is no longer there, then this arrow will also be no longer there. Everything else will go through.